Hello, and thank you for joining us for the sixth annual Global Summit on Kidney Disease Innovations, Vox Populi. The time is now to prevent and cure kidney diseases. This summit is hosted by the American Association of Kidney Patients in partnership with our allies from the George Washington University School of Medicine and Health Sciences. My name is Edward Hickey, and I have the honor of serving as president of the American Association of Kidney Patients. I'm an attorney from California, and I'm a chronic kidney disease patient and have experience as a care partner due to the history of kidney disease within my family. Early detection and timely innovation are pivotal to managing kidney diseases, which affect 850 million individuals worldwide. The adoption and implementation of early screening recommendations and protocols is a strategic priority for AAKP and the global kidney community. The fact is that early screening and early intervention limits the burden of kidney disease on people, family, taxpayers, and health systems. AAKP has spent years advocating in the United States for a federal government recommendation to screen early for kidney disease. Right now, the U.S. Preventive Services Task Force is still debating whether there is enough evidence to support such a recommendation. As patient advocates, we believe the evidence already exists, and you can find it among the millions of Americans whose lives and livelihood have been disrupted by a late diagnosis of kidney disease. Evidence is also found among the millions of families who have lost a loved one to this devastating disease that could have been prevented or better treated. We believe the failure to adopt a national screening recommendation is a negative government determinant of health that must and will be reversed through advocacy. But outside of government, there's an overwhelmingly positive news. Innovation is driving a new generation of highly sophisticated diagnostics and medical practices that result in earlier disease detection. Today, we will hear about some of these new technologies and share valuable insights on how advancements in early screening techniques and care practices will transform patient care. We will explore the latest research findings, practical applications, and the impact of these approaches on patient care and patient lives. With that, I'm honored to serve as the moderator for our session entitled Utilization of Early Screening and Enhanced Standards to Support Early Identification and Intervention of Kidney Diseases. It is with great pleasure that I introduce our next speaker, Dr. Richard Dorshow, a scientist and innovator in the field of medical diagnostics. Dr. Dorshow is the Chief Scientific Officer, President, and co-founder of MediBeacon, a leading company in the development of cutting-edge technologies for medical imaging and diagnostics. Dr. Dorshow's extensive expertise and groundbreaking work have made significant contributions to the advancement of early screening and enhanced standards for the identification and intervention of kidney diseases. His leadership at MediBeacon has driven the development of innovative solutions that promise to transform how we detect and manage kidney conditions, also patient outcomes. Today, he will discuss his company's breakthrough device that is intended to measure GFR in patients with impaired or normal kidney function. Welcome, Dr. Dorshow.
Well, hey, I want to thank Ed. I want to thank the AAKP for inviting me. I want to thank George Washington University for hosting this event. I'm Dr. Richard Dorshow. I'm the Chief Scientific Officer at a company called MediBeacon that I co-founded a few years ago. Full disclosure to the audience here, I'm actually a trained physicist. I am not a nephrologist, but in developing a new measurement for GFR, I've talked to many patient advocate groups and have come away with the knowledge that many of the actual patients aren't quite understanding how their nephrologist actually measures eGFR. And I think this would be a great illumination to the patient. So I want to go over how the nephrologist actually calculate and tell you what your eGFR is. It is not an optimum measurement. There are optimum measurements, but they are rarely used because they're time-consuming and laborious, and I will go over that. And then I will go over how our new measurement, our transdermal GFR measurement, combines the optimal measurements that the community would like and that the FDA guidelines also show, and should be way better for the patient community. So classification of kidney disease is by GFR, and as you see in this little picture on the right, and if you know anything about your numbers, and if you're in between 120 and 60, you're essentially thought to be in the normal range. And in this classification system, that's stage 1 and stage 2 of the GFR ratings. Anything above 60, usually there are no interventions, but if your numbers are between 60 and 15, you're thought to have chronic kidney disease. There are different interventions. If you're in that stage 3, you get certain interventions. If you're in that stage 4, you get even more interventions. And it's that number at 15. If you're less than that, you're said to be an end-stage renal disease, and you're either have to be on dialysis, or that's when you get to be on the list for transplant. There's another way to categorize this. This is by the NKF, and essentially what they have done is that once you're below the normal range, that stage 3, they've divided that up into essentially a 3A and 3B, just so that you could see that as soon as you kind of get into the impaired renal function area, there are interventions that can be done. If it gets worse, there's more interventions and more interventions. So it's just a way to kind of categorize the staging of the disease and the interventions that are usually done. So let's go over the current standard of care, and that's an eGFR equation based on serum creatinine. So serum creatinine is an endogenous compound that your muscles make in your body, and is taken out of the body by the kidney. So if everything is okay, every day you're making some serum creatinine and your body is taking it out. So the level of serum creatinine stays constant. It's when your kidneys start not functioning, becoming impaired, that compound starts building up in your body, and that's how the eGFR is staged. So you take the values that you get for the serum creatinine, which you get from just a single blood draw. The nephrologist puts it in various equations and spits out an estimated GFR. So you can see in this example, the estimated GFR is 115, which is in the normal range. However, there are many just well-known issues with serum creatinine as being a surrogate for kidney function. I've listed 3 of them here. First of all, upon any kind of kidney insult or injury, it may take a day or 2 days for the serum creatinine to actually detect that kidney insult or injury. In other words, it'll take a day or 2 for the serum creatinine to build up in your body to show it's been injured. And it's not a sensitive measurement. You could lose half your kidney function before the serum creatinine values or levels rise above the normal level into an abnormal level. So that's why it's kind of a silent kind of sneaking up disease. And then finally, there are other factors that affect serum creatinine that are not related to kidney function. And some of the those attributes are listed there: age, how well you're hydrated, muscle mass is really important, and diet. Is eating a lot of protein actually adds to the serum creatinine. So once the serum creatinine number is established for a patient, it gets put into an eGFR equation. Now, these eGFR equations have been developed as ensemble averages over equations developed from 5,000, for example, 3 to 5,000 people, and that's what all the little gray dots are on this graph. But what you need to take away from this is in the upper kind of right-hand corner, and you can see it also on the x-axis of the graph here, the bottom axis. If your estimated GFR is at 60, well, the actual GFR could be plus or minus 30. So your GFR could be 30 mils per minute or 60 mils a minute, but your eGFR will say 60. And that's why, although the eGFR is ensemble average, it's not necessarily accurate for an individual patient. So that is what many of the patients I've talked to have run into and have issues with. So let me summarize again, because I think this is really important. This is something that each of the patients really should know. Again, the serum creatinine, it's not a sensitive measurement. You can lose half your kidney function before you see an abnormal level. There's a rather large time delay if you have an injury and insult to the kidney, and the serum creatinine won't show that. In fact, it's been shown that in some kidney transplants, if you take one kidney out and you keep on measuring the serum creatinine, you don't see a change for a day or two. And again, there's those factors that are unrelated to kidney function that affect the serum creatinine. And as for the equations themselves, right, the equations depend on some of these other attributes. And I put one of the equations that's been used over the last decade and a half, but you can see in the factors where it says GFR equals, there's terms that depend on age, there's terms that depend on gender, and there's terms that depend on race, which has been a big controversy over the last, I'd say, 5 years. So you can see how it's not an ideal measurement, especially for an individual patient. There are optimum measurements of GFR, right? And so these are not using the endogenous compounds of the body. These are using an exogenous compound, which is something that gets injected into you, usually IV, but is known to be cleared from the body by the GFR mechanism of the kidney. One compound is radiolabeled iothalamate. I bring that up specifically because that's really the only FDA-approved exogenous GFR agent. It was approved back in 1974. But then there's also inulin, which is a product of plants, which is used previously quite a bit. And then there are the small X-ray agents, iohexol and iothalamate. There are the MR, the magnetic resonance contrast agents. And then there are at least 2 radioactive agents, all of these of which have been shown to be GFR agents. And they give you an actual true GFR because you're injecting them into the body and you're measuring the amounts coming out of the body. And that gives you the GFR, not an estimate, a direct measured value. The issue with all these is that you have to take blood samples over time after they've been administered to the body, and then you either have to measure the concentrations of these agents in the various blood samples as a function of time using rather sophisticated laboratory equipment, and it requires a lot of sample preparation. And also the ones that are radioactive, they have a major drawback in that, it's hard to handle them in routine measurements, in the hospital, in the ICU. So mainly these optimum measurements have been used for research purposes. And just to kind of hit home one more time, these optimum measurements, they exist, but they're not clinically amenable, right? They all require blood draws, which is invasive detection. They all require sample preparation, which is laborious. And again, the radioactivity or the sophisticated laboratory equipment that's needed to measure the concentrations make these all not amenable to the point of care. So again, they're mainly used for research. And just to highlight for hopefully the last time here, again, there's radioactivity involved in these optimum measurements. There's blood draws, and the ones that require sophisticated laboratory equipment usually can be done only at research type institutions like the Cleveland Clinic, the Mayo Clinic, or the NIH in Bethesda, or a very few others. They're not amenable to the usual standard hospital, even academic hospital settings. Now, what we have done at MediBeacon is come up with a new agent that can be measured directly. That would be considered an optimum GFR measurement category. That's this molecule here we call romapyrazine, but we've shown it to be a GFR agent in humans, but it also fluoresces. So there's a 2-prong effort on this new measurement. We've got a fluorescent agent that actually is a GFR agent, and we can measure it transdermally through the body at the point of care. So this is the novelty of what we've done, and hopefully we'll show you here why it will hopefully impact patients that rely on a GFR for various interventions and treatments and transplants, right? And again, it's got all these properties listed on the left there that one needs for a GFR agent, like all the other optimum exogenous agents. But here we just have to illuminate the skin with blue light. The agent, as it's going through the body, glows green, and that's what we detect. In order to show that this new compound is a GFR agent, we did a clinical study where we looked at various subjects who had different GFRs, the whole range. In the upper left, you see data from a subject that had normal renal function. The red dots are the various concentrations from the blood samples we took. The little blue line is a fit to a pharmacokinetic model that yields GFR. Well known, everybody uses that. And then in the bottom right, you see somebody with extremely impaired renal function. And again, you've got all the blood draws and concentrations, but the line there is really shallow, giving us a very low level of GFR. And again, you can see in the upper right, the agent, since it's a normal renal function, is coming out quickly. That slope is really steep. Bottom right, the subject has impaired renal function. It's coming out really slowly. So even after 12 hours, you still have a lot of the agent in the body. In order to actually show that it's a GFR agent in humans, in this particular clinical study, we administered our agent, romopyrazine, and quickly followed by iohexol, which is what we agreed with the FDA would be used as the standard of truth. And so you plot the GFR of our agent versus GFR iohexol. You see you get this perfect, almost perfect correlation. So perfect correlation here, the slope of that line would be 1, and you can see it's as close to 1 as you can get, 0.994. And the goodness of fit, perfect would be again 1, and we get 0.998, which is as close as you can get. So we've established both in the literature now and in the and with the FDA that our new agent is a GFR agent in humans. So that establishes the first objective we need, is to show that the agent actually is a GFR agent in humans. And now we go on to show the transdermal attribute of it. All the subjects in this clinical study were enrolled by EGFR. So we had the EGFR of everybody, and that was so we can get subjects that span the GFR range. But then we did the measured value, right? And so if you see on this graph here, and it's not terribly important to understand exactly the graph, but on the y-axis is the EGFR we measured to screen the subjects, and the bottom is the actual measured GFR. All the green dots is where the EGFR values actually were equivalent to the measured GFR values. The yellow dots are the subjects where the EGFR was different from the measured GFR value by 1 stage of chronic kidney disease. Right. And so what we found, and if you look in the table in kind of the upper left, 64% of the subjects, the measured GFR matched the EGFR, but almost a third of the subjects had an actual measured value of GFR that differed by 1 CKD stage than what the EGFR said. And again, it's the EGFR that the nephrologists have been staging kidney disease. So you can see why a measured value is really important and impactful. So this is the basis of our new measurement system. We call it the transdermal GFR system. So we use the new fluorescent tracer. It gets administered to the body. We have a sensor that's placed on the skin that you see connected to the display monitor that's on the right. So coupling the fluorescent tracer agent with transdermal detection enables an actual measured value at the point of care while it's happening. It's not a delayed measurement where you have to put samples in a radioactive counter or use the sophisticated laboratory equipment to measure concentrations. This is can be all done at the point of care. In fact, the monitor here is like on an IV pole we had the subjects in our clinical study were next to. Right. And so again, here's kind of how it works. So, the little flesh-colored rectangular box there in the middle is kind of an avatar for your skin. The patch that we put in the skin has a blue LED that activates the romopyrazine as it's going through the body. It emits the green light, and it's that green light that we measure. And as the kidney is taking the agent out of the body, the concentration is going down, the green light decreases as a function of time, and it's that decrease of this green light that we can convert to a TGFR, which we call the TGFR for transdermal GFR. Here's some of the data from our clinical study. On the left side, you see it's a plot of the fluorescence that we're measuring versus time. And this is for a subject with normal kidney function. The blue is the actual fluorescent data that we're taking. The red line is, again, a fit to a two-compartment model, a pharmacokinetic model, where it's that straight line that yields the GFR from our computations, right? And so if you've got normal kidney function, before we lose signal to noise, we can measure out to 8 hours with one injection. It's a continuous measurement, so we can be giving you a continuous GFR the whole time. On the right side, there's a subject with impaired kidney function. So again, a bolus administration of our agent, you get the data with that straight line, but it's very shallow. So you can see, even though the clinical study here, we ran out to 12 hours, somebody with impaired renal function, we could run that out to 18 to 24 hours with one administration, having the monitor give us a continuous GFR over the whole time. Then one of the main attributes here is that because we're measuring transdermal through the skin, the actual skin color doesn't matter. So in this clinical study, we recruited people with various skin colors. There's a scale called the Fitzpatrick Skin Scale that divides the human race into 6 skin colors. Recruited people with, in each one of those buckets. So this graph is showing the light skin versus the dark skin, and you can see in this graph of our measurement, TGFR on the x-axis versus the actual plasma on the y-axis. The two groupings essentially are the same. We get the same analysis through that. So this just shows that our technique is independent of skin color, which again, last few years has been a rather large issue that the nephrology community has been grappling with. Right, so let me go over just one more time. Again, this new methodology that gives us an actual measured GFR is independent of skin color, independent of gender, independent of age. It doesn't depend on the concentration of various endogenous blood compounds. Also doesn't depend on height and weight. And so all these various attributes are necessary for the estimated GFR calculations. So a massive advantage to doing this new technology. This is an animation of what we like to call our point of care transdermal measurement. So you put the patch on we put it on the chest. First thing it does is it determines the skin color. So it changes the LED power and the amplification. It gets injected into the vasculature. It equilibrates between the vasculature and the tissue. And once that happens, once you get an equilibration, we're able to start calculating the GFR, and it starts spitting out the GFR values on the monitor. You can go to a screen where you're seeing the fluorescence versus time, which is what you see right now. And again, as this is happening, it's calculating every 15 minutes or so a GFR, and it spits it out so you can see a full history as you're going. And again, if you got normal renal function, we tend to go out to 8 hours, but if you got impaired, we can go out, much longer. But essentially, this is how the system works. It also gives you an estimate at the very bottom on how long you have until the agent is depleted and the measurement sense is over. So almost lastly here, so what is the indication for use? Essentially, just to measure the GFR in patients with impaired or normal renal function by monitoring the emission of our agents. So that kind of covers everybody. There may be a little caveat on the indication because in order to show that it works, we had to use patients with stable GFR because we had the standard of truth was a blood draw, and so that'll just be noted that in patients with stable GFR. Lastly, what would be the impact to patients? And this came from talking to various patient advocate groups. There's just been a lot of the patients that have been negatively impacted by an eGFR measurement and have said if they had something like this measured GFR, they would have had a more positive, or at least a less negative outcome. What this methodology does is eliminate the racial bias of some of the eGFR equations. And then you can imagine some of the impacts. And there's just a couple I've outlined here, but if your EGFR has told you that you're not eligible to donate, that could be wrong. A measured value could tell you that, maybe it's higher than the EGFR and that you could donate. Conversely, for subjects who want to donate, if your EGFR says you're in a region where it's okay to donate, but you actually do a measurement and it's lower where you shouldn't, this will let you know. Also, an accurate measurement is important for those whose maybe initial kidney transplant is failing, and it's like when should you do a second one? And what we really hope, and the advantage to maybe millions of people, is that by using this, since it's so simple and can be done at the bedside, you can identify early changes in the GFR, and the earlier the changes identified, the earlier the interventions, and the earlier the interventions are able to be done, the better off you will be in trying to preserve kidney function. And almost every patient can now kind of look to what they've done and see where this could impact themselves. And I think for now I will stop there. And again, just thank everybody for allowing me to present what we've done and how we believe it'll start impacting patients in the near future.
Thank you, Dr. Dorshow, for your informative presentation. I have a few questions I'd like to ask you. Dr. Dorshow, can you tell our viewers how critical the creation of objective standards are to the advancement of innovation in diagnostics? AAKP believes this is often an underappreciated part of developing new products and clinical care standards in kidney medicine.
Oh yeah, no, I believe wholeheartedly in that that endeavor, right? In order for us to compare, right? And I just went on and on about trying to compare EGFR with an actual measured value. There has to be some kind of standards, and some of the compounds I talked about have been acknowledged standards, but that keeps on changing, right? So in this particular field of looking at measured GFR methodologies, for example, inulin, years ago was thought to be the best thing that could be done for measured GFR, and then it became hard to find that, right? And so then people were coming up with other standards, such as the small X-rays that we used here, the iohexol. But in order to make progress, there has to be some kind of standard that you say this is as good or this is better. And hopefully with the examples I showed, you could see where exactly that has taken place. In order for us to develop something new, we had to compare it to something that everybody agreed to was a standard or as close to a standard as you can get, and therefore this is shown to be better.
Dr. Dorshow, can you tell us how the voices of patients, especially the unmet care needs of underserved people, helps inform the sense of urgency in science and standards development?
Let me do that from our experience when we started talking to the various patient advocate groups and the representative patients that were there. We could immediately see the impact of what was the current care. For example, in our case, the estimated GFR and how it was affecting every patient, right? Because everybody gets staged in terms of their chronic kidney disease and the interventions they're getting by that. And some people actually knew that the numbers that they were getting were not actually indicative of what they could feel in their own bodies. Again, because the actual value, if you had done a measured value, doesn't agree with the estimated value. So it was discussions with many of these patient advocates that certainly bolstered us to continue doing what we were doing and seeing where the importance actually lies. And so we were really fortunate, or it's to do that, to talk to so many patient advocate groups, including the AAKP was a major was who we talked with a lot.
The theme of this year's Global Summit is Vox Populi, We believe patients around the globe have spoken about the unmet need to transform kidney medicine and improve patient outcomes. Can you tell us how the voice and insights of patients have informed your commitment and contributions to kidney medicine?
Yes. Well, in our discussions with actual patients, as kind of I said before, we understand how our new technology can impact almost every individual patient, and it certainly has spurred us on to finish what we're doing, right? And so. Most of the technology I've talked about here as it applies to humans is still under development. We're still pursuing FDA approval, hasn't been approved yet. And this is a rather large effort to do this. It involves many people within our company, and everybody's effort has been redoubled to achieve that goal, again because we have seen how it can impact almost everyone we talk to who is in the patient advocate groups, some of which were U.S. based and some of which were internationally based.
Thank you, Dr. Dorshow. This is certainly exciting news for our community, and AAKP looks forward to supporting your efforts to bring this technology to patients.